Okay, just finished up chapter 1. Now we're going to start with chapter 2. Chapter 2 is on inductive reasoning and conjectures that come from inductive reasoning. All right, today you'll be able to apply inductive reasoning to a pattern to determine a conjecture with the given information. Now, first thing you need to know is inductive reasoning. Inductive reasoning is based on patterns you observe. So inductive reasoning is based off of patterns you observe. Okay, let me show you a couple example problems right here. If you look, 1 to 4, 4 to 9, 9 to 16, 16 to 25. You'll notice that it's not increasing by a specific number each time, but the number that it increases changes. But look at the pattern. It increases by 3. This increases by 5, by 7, by 9. So the next increase is going to be by 11, which should make the number 36. And then from there, it's going to increase by 13, which is going to make it 49. By the way, if you didn't notice, these are actually the perfect squares, because this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and even 7 squared. So that's another thing. Now, if you look at down below, down here, increases by 4, increases by 8, increases by 16, increases by 32. So the amount that it increases by is that. There's also another pattern here. You could also take, this number, subtract by 1 to get that, subtract by 1 to get that. So this will increase by 64, which means it'll be 127. And then this will increase by 128, which will make this number 255. Now, that's the pattern you see. Does that mean that that is going to be the exact outcome? No. I'm highlighting these in green so that you see that those are the pattern. All right. Now, that, like I said a moment ago, that doesn't mean that that has to be the outcome, but that's the predicted outcome. It's reasoning, logic based on what you're seeing. Now, the same goes down here. Same goes for this one. I have a triangle. I have a quadrilateral. I know you're thinking that's a square, but we don't know if it's a square. We don't know if the sides are equal. We don't know if it's right angles. So that's one thing about geometry is you can't go by what it looks like. You have to go by the evidence. The only thing that we do know is that this is a four-sided figure, so it's quadrilateral. So that's pentagon. That's an octagon. Now the next figure is going to have 7 sides. Let me rewrite that again. It's called a septagon or heptagon. It's 7 sided. Well, right after that is an 8-sided figure called an octagon. All right. Now remember, an octagon, probably the most prevalent octagon you're going to see, you see it every day on your way to school. You see stop signs. Those are octagons. Now for the next one, if you look, shade on top, shade on right, shade on left. What's next? Or sorry, shade on the bottom. So next should be shade on the left. Now, just remember, my drawings aren't the best. So there you go. That's the next pattern. Same thing down here. 1 circle, 2 circle, 3 circles. 1, 2, 3, and 4 circles. Okay. So you see how this formed. Now remember, inductive reasoning is based off the patterns. So this is the pattern. That's the predicted outcome. Now, the conjecture, all those things that we came up with previously are called the conjecture. It's a conclusion based on inductive reasonings. Now, the examples are what we just said. These are examples of conjectures. Conjecture, and another conjecture. So those are what a conjecture is. So now here's an example. The Perry Morgan High School cafeteria served chicken nuggets the first 4 Thursdays of the school year. Today just happens to be the Thursday of the 5th week of schools. The conjecture is we'll be having chicken nuggets today in the cafeteria. Does that mean it's going to happen? But that's what we're predicting. Or another example I like to use. The Perry Marion High School basketball teams are made up of tall students. John is tall. So the conjecture, if John is tall, then that means that he's going to be on the basketball team. Does that mean that that's going to happen? Not always. Sometimes yes, sometimes no. It's a conjecture or a prediction. As a matter of fact, I do have a good friend by the name of John who is very tall and doesn't play good basketball. I can't complain. Neither do I. I was horrible at basketball. I love watching the game, but it's not my game. Some of you are great. That's good. I'm not, and neither is John. Anyway, that's that. So a conjecture, and I'm going to highlight this for you, is a conclusion based off of inductive reasoning. All right, so now, just a moment ago, we stated that not all conjectures are going to be true. There are times when conjectures will be false. So once again, a conjecture is a conclusion based off of inductive reasoning, but a counterexample is an example for which the conjecture is false. Now, here's what you need to know. In order for it to be true, a conjecture has to be true in all cases. Let me repeat that. A conjecture must be true in all cases. In order to prove it false, you only need to prove it in one instance. You only need one false example to prove that a conjecture is false. All right. Now, I love using this example every year. Geometry. This is and actually I'm going to write this over here. This is my conjecture. Actually, let's use green. Conjecture. The conjecture is this, and I'm going to underline it. Geometry is a sophomore level class. So the conjecture is every student in this class is a sophomore. Matter of fact, let me fix that real quick. All right. You see it right there. I missed it. So a statement is geometry is a sophomore level class. That is a true statement. So every student in this class is a sophomore. I would ask you, prove me wrong. A bunch of you would raise your hand. Some of you would say, I'm a freshman. That's a counterexample. Some of you might say, well, I'm a junior. That's a counterexample. So any student that is not a sophomore in this class is a counterexample to the statement that every student in this class is a sophomore. So any freshmen? Any junior? Or by chance, any seniors? And by the way, over the years, I have had juniors and seniors in this class who have decided to retake the course for a better grade because they may not have understood it when they took it as a freshman or sophomore, and I'm perfectly fine with that. Matter of fact, I enjoy having them because they have the experience and they're able to help the younger students who are taking this for the first time. So that's always a good thing. All right, now Another example is, if n is a real number, then negative n is a negative number. Now remember, n can be any number. So I need a value of n that will make this statement false. So the conjecture is actually right there. That's the conjecture. Then n is a negative number. Well, I need one counterexample. The counterexample is this. Here's the counterexample. What if n equaled -2? Let me rewrite that again. What if n equals -2? Because if n equals -2, then negative n would equal the opposite of -2, which is +2. That's my counterexample right there. That right there has proved it wrong. And you don't have to just use negative. You can use any negative number. You can say even 0. Because remember, 0 is neither negative or positive. I know there's always been a debate. Remember, 0 is just 0. So, and with that being said, let's do one more example and then you are going to be done with this lesson. All right, so once again, a conjecture is a conclusion based on inductive reasoning, and a counterexample proves that statement is false. So here's what we have. If angles ABC is congruent to angle DBE, then angle ABC and angle DBE are vertical angles. Okay, how do you disprove that statement? With one counterexample. All I need, A, B, C, and I can draw it such that they both have the same vertex, which would be point B. So I'm going to draw it from right there to right there. We'll say that's point D and that's point E. You see, both angles are congruent, but they're not vertical. Remember, this is what it would look like if they were vertical. This is vertical. This right here is vertical. We don't need that. So I'm crossing it off. This, on the other hand, is, for some reason I got deleted, so I'm just going to draw it there. There we go. Okay. See, these two angles are congruent, but they're not vertical. That's all I need. Sometimes you have to draw it in order for it to, in order for that to work. Okay. So that's lesson 2.1. Email me if you have any questions. We'll talk about it in class. In the meantime, you can now start working on homework quiz 2.1.